Hi there and welcome. This video is on section 10.2. I'm going to be showing you how to do calculus using parametric equations. So this is after the previous video, section 10.1 on parametric equations. So if you want an idea of what a parametric equation is or how they relate to regular Cartesian equations, please check out that video on 10.1. I'm going to jump into the calculus, assuming that we're a little bit familiar with what parametric equations are. Okie doke. So I have here a couple of parametric equations. And in this example, I want to find the derivative. Now, x and y are the actual variables here. T is a parameter, so we're not going to find the derivative in terms of t. We're either going to find dx dy or dy dx. Let's go ahead and find dy dx. It doesn't specify, it just says find the derivative. So it would be nice if it's specified, but let's see if we can find dy dx. That is a lot of times what people would interpret as the derivative. All right, so how do we find this? Dy dx means we're differentiating with respect to x, but these equations are in terms of t. So what do we do? Well, we actually do what's called the chain rule. So if you remember the chain rule, you have some function, some inside function, right? And we differentiate that inside function with respect to whatever this thing is. We call the inside function u sometimes. So we differentiate the function with respect to u. So maybe we'll differentiate the function with respect to u, and then we multiply by the derivative of the inside function. So du dx. And what comes out of that is we get the derivative of f with respect to x, or if you want to call this y, we would get the derivative of y with respect to u. This should be a u, by the way. Derivative of y with respect to u times the derivative of u with respect to x, and you can see the du's divide out, and you get the derivative of y with respect to x. Another way of seeing this is just algebraically. If you take dy du, and then you times du dx, the du's are going to divide out, and you get dy dx. This is the same thing as taking dy du and dividing by du dx. Excuse me. Let me change this. Dividing by dx du. All right, so how do I know this is right? Because to divide by dx du, we would then flip and multiply. So this would be equal to dy du times the flip of dx du, which would be du dx. And then the d's would cancel out as usual, and you get dy dx. So this is really what the chain rule is all about. You just have this intermediate variable. They called it u, or the inside function, and then you differentiate with respect to the inside function, and then you multiply by the derivative of that inside function. The derivative is the chain. So that's our general idea. So let's translate this into t's. Instead of using u, let me use t. So dy dx is going to equal dy dt divided by dx dt. All I've done is taken this equation right up here, and I've just written the u's in terms of t. So it's the same equation. I've just written dy dx in terms of dy dt over dx dt, and you can imagine flipping and multiplying and stuff like this. But this, my friends, is the formula you will find in the book with how to find dy dx if you know y in terms of a parametric variable like t, and x in terms of the parametric variable t. So we have x in terms of t and y in terms of t. All we have to do is find dy dt and dx dt, and we could fill it in to find dy dx. All right, let's go ahead and do that. So taking my equations over here, I have x equals, move me up a little bit. Oops, not bigger, out of the way here. Okay, we have x equals t to the fourth plus 2. So I can differentiate everything respect to dt. That gives me a dx dt. And the derivative of t to the fourth is 4t cubed. I wouldn't get any differential because it's really dt over dt if you want to think of it that way, but that's just 1, right? So we don't write any of that. The variable matches the differential. So dt over tt, that just becomes 4t cubed. And the derivative of 2 is just 0. So then now we know what dx dt is. Oops. Now we know what dx dt is. And we do the same thing for y. So y is t cubed plus 1. We differentiate everything with respect to dt. And we get dy dt is equal to 3t squared. Okay, so then we can fill in our formula here. Dy dx is dy dt, which is 3t squared, divided by dx dt. Dx dt is 4t cubed. So that's the dy dt over dx dt. And it looks like we can simplify this a little bit to be 3 over 4t. So our dy dx is expressed also in terms of this parameter. Dy dx is 3 over 4t. And that's how you can find the derivative of a function when it's actually being represented by parametric equations. And this also works for non-functions, by the way. So you can find the derivative of anything using this technique, right? By differentiating the x and the y separately and then dividing the two. All right, so what can we do this? Well, we can do all the stuff we've been doing with calculus up until this point, like find the equation of a tangent line. To find the equation of a tangent line, you need a slope and a point. So we need to find a slope. We need to find a point. The point we already given is 3, 2. And to find the slope, you just have to find the derivative. The derivative finds all possible slopes of all possible tangent lines. We need to find the derivative at the point 3, 2. That will give us the slope of the tangent line at 3, 2. Well, we know what the derivative is. The derivative we just found, this is the same equations as above, right? I didn't change the equations. So the derivative, dx dy, is 3 over 4t. And now all we have to do is just plug in the 3 and the 2, and we get our slope. Problem? X is 3. There's no x's in here. Y is 2. There's no y's in here. We need to find out what t is because we don't know how to calculate dy dx unless we know which value of t to plug in. All we know is x is 3 and y is 2. We don't really know what t is. And that's important because our derivative is written in terms of t. But don't fear, we know what x and t and y and t, we know how they're all related because we're given the equations right here. We're given the equations of how they're related. So if x is 3, then I can write this as 3 equals t to the fourth plus 2. And if y is 2, I can write this as 2 equals t cubed plus 1. And I could just solve for t. Now, these have to match up. I can't have one equation having t equals 3 and the other equation having t equals 4. It's got to be a t value that gives the point 3, 2. And this is important because we're dealing with non-functions. There could be different, x values, different y. They could have 2 different y values for the same x value, etc. Right? So we really make sure that the t's match up. So I'll just do a little algebra here, subtracting 2 on both sides, taking the fourth root on both sides. Because it's an even root, I'm going to get an absolute value or a plus or minus if you want. So I get plus 1 and minus 1 are the values of t that give x is equal to 3. What about in the y rule over here? I'm going to subtract 1. I take the cube root. I guess I should be writing this as the fractional exponent because we don't really do roots in calculus. So I'll write this as 1 to the 1/3 exponent is equal to t. There's an absolute value because it's an odd power, and 1 to the 1/3, if you're only using real numbers, that value is 1. So the only one that matches up here is t equals 1. So we know that t equals 1 is the value that corresponds to x is 3 minus 2. So I'm going to write t equals 1 over here. And that means that our derivative at 3, 2 and t equals 1 is just 3 over 4 times 1. So we know the slope is equal to 3/4. Now that we know the slope is, the point is 3 comma 2, and the slope is 3/4, we could just go ahead and find the equation. Most of you at this point are using the point slope form of equations, of linear equations, excuse me. So tangent line equation, it's a line, so it's y minus y1 equals m x minus x1. We know the y value is 2. We know the slope value is 3/4, and we know the x value is 3. I'm going to move the 2 over so that it's in y equals form. And there we go. That's the equation of the tangent line. All right. So, as long as you understand how to find the derivative and, the fact that you have another variable here, t, that you have to sort of think about, very similar in strategy in terms of what we did before when we were just finding tangents of Cartesian equations. All right, another thing we did when we had our xy equations is we find area between the function and the x-axis. That was the integral. So we're going to do that as well. In this case, we have this parametric equations, same parametric equations, by the way. We're going to find the area between those parametric equations and the x-axis. So just kind of a visual idea here. We have these parametric equations, which could be any weird kind of thing, right? It could be any kind of weird thing. I'll just draw something like this. We need to find the area between this and the x-axis. Oops, I didn't put some limits on this thing right here. So I neglected in my lecture notes to put what the values are. So I'll just sort of, I think it was like 0 to 1 from t equals 0 to t equals 1. I don't have my notes next to me, so I'm just going to make up t equals 0, t equals 1 on the fly. And just say we're going to find the area between the parametric equations and the x-axis from t equals 0 to t equals 1. All right, so we got some funky function or non-function. We got some graphy thing. We got the x-axis. So this is the x-axis right here. And we're trying to find the area in between. So this area right here between the parametric equation and the x-axis. So how do we do that? Well, what we did was we divided this up into little rectangles, right? This is called a Riemann sum, right? Lots of rectangles, all like infinitesimally thin. The thickness or the thinness of it was called delta x or dx. And the height of each of these rectangles has a height of y. Right? It's y up, and it's a super thin dx wide. So the area would equal, well, the area of a slice is just y times dx. So the area of all the slices would be the integral of y times dx. And we'll say we're going from t equals 0 to t equals 1. All right, so that's all we had to do, just like we did before. Although, once again, it's going to be looking a little bit different because we have parametric equations. We don't have a Cartesian equation. But let's go ahead and do it. We know what y is. Y is right here. Y is t cubed plus 1. So the area is equal to 0 to 1. This is t equals 0 to t equals 1. And y is t cubed plus 1. And then we have dx. The reason why I'm putting the t's here is to emphasize that we cannot just anti-differentiate this, because everything's in terms of t's except for this critter right here. That's a dx. That's not a dt. We need a dt there in order to do our anti-differentiation formulas. So we need to convert dx into dt. But we've done that lots of times before. We did that most recently in substitution, where we did, we had to change variables. So we know what x is. X is t to the 4th plus 2. We're looking for what dx is. We can find dx just by taking the derivative. I'll take the derivative with respect to t, since the right-hand side is in terms of t, and because I want a dt in my answer. So differentiating this whole thing with respect to t, I get dx dt on, to t, I get dx dt on the left-hand side. On the right-hand side, I get 4t cubed plus 0. And this just solving for dx, just moving things around. I get dx is equal to, oops, I'll put the dx on the left-hand side because that's where it is. Dx is equal to 4t cubed dt. So now I can take my dx thing and put it right in there. So then I can rewrite this equation. Area 0 to 1. Everything's in terms of t now, so I'm just going to leave off the t's. T cubed plus 1 times dx, which is 4t cubed dt. Now we have an equation, we have an integral with everything in terms of a single variable t. And now we can just go ahead and do our normal calculus. I'll just simplify this first by distributing. That is t cubed times 4t cubed, which is 4t to the 6th. And then 1 times 4t cubed is 4t cubed. And all of this is times dt. These are nice, simple power rules or polynomial rules. So the integral of 4t to the 6th is 4 over 7t to the 7th. And then I get t to the 4th over 4. So 4t to the 4th over 4. So I guess these 4s don't have to be here anymore. I get a plus c, but the c is going to go away. I just need to evaluate this at the t values of 0 and 1. All right, I'm going to plug in t equals 1. So if I plug in 1, I get 4 over 7 plus 1. That's when I plug in 1. And then I subtract when I plug in 0. And my area is 4/7 plus 1, which is also known as 11/7. So that's the area between this parametric equation and the x-axis from t equals 0 to t equals 1. All right, so just kind of keep track of your variables, your x's and t's. Make sure that you set up everything the way it's supposed to be set up, and you get the right answer. Let's do a few more problems before I end this video. So another area one, where again I forgot the values of t. So I'll again say t. Oh, I put the t values over here. So I remembered it some places. So we'll do t equals 0 to t equals 1 for this one over here as well, because I just forgot to put the t values right. So the area is infinite if you don't have any bounds on the t's. So find the area between this function and the y-axis. It's very similar to the previous problem. The previous problem I had us find the area between this parametric equation and the x-axis. It's the same set of parametric equations, I believe. And we're just supposed to find the area between it and the y-axis. This is a perfect time to give this a try if you are feeling up to it. And see if you can figure out how to do it. It's not exactly the same, but it's certainly similar. So please pause if you're willing and give it a try. And I'm going to show you the solution for those who are coming back or just wanting to watch me solve this problem. So once again, I have some weird function thingy thing or non-function. I have some weird graph or something. I'm trying to find the area between it and the y-axis. So this is the y-axis up here. And so I'm going to be drawing sort of this over here and this over here and finding this area between this parametric equation and the y-axis. So instead of putting a smudgy thing there, I'll just remind you that all we're doing is just doing rectangle sums, right? All these are little rectangles. Each rectangle has a vertical width, which is very, very small, called dy. And each rectangle has a horizontal length, which is called x. And so we know the area is equal to the rectangle, right? Each rectangle itself is just x times dy. And then we need to add them all up because there's a whole bunch of them, an infinite number of little rectangles. And that's our area between this parametric equation and the y-axis. Now we are going from t equals 0 to t equals 1, as I specified recently. And so now all we have to do is to find the integral. We do need a single variable. We have t, we have x, we have y. It's going to be easy to put everything in terms of t. So let's go ahead and do that. So we get t equals 0, t equals 1. I know what x is because I was told x is t to the 4th plus 2. And I can find dy just by doing a little derivative over here. I know y is equal to t cubed plus 1. So dy dt is equal to 3t squared, or dy is equal to 3t squared dt. So instead of dy, I'm going to put my 3t squared dt. And that's my integral that represents the area between the equation and the y-axis from t equals 0 to t equals 1. And now we just do our normal calculus formulas. I'll do some of it. I'm not sure at this point whether I'll do all of it. Maybe I'll leave it as a quick exercise. This becomes 0 to 1 of t to the 4th times 3t squared is 3t to the 6th. 2 times 3t squared is 6t squared. And then I got a dt here. And then you anti-differentiate, plug in the 0, plug in the 1. I think I'm going to let you guys finish that problem. It's very straightforward. You just use the power rule for integration, plug in the 0 and the 1, subtract, and you get your answer. So I'll leave it like there. If you really want me to go through the last steps or you want to check your answer, just let me know and I can show you off video. All right, let's trudge on to our last couple of examples so we can try to keep this video a little bit shorter. Okay, next it says find the arc length of these parametric equations, same parametric equations, and I have t equals 1 to t equals 2 for this particular arc length. So what was arc length? Arc length was a thing where we had some kind of function, or yeah, we had functions before, and we were trying to find the distance along the graph by splitting it up into little pieces, right? So we're not splitting the x-axis, we're not splitting the y-axis, we're splitting up the function itself into little pieces. And each one of these little pieces was called ds. S was somehow chosen to be the letter for the distance along a function. And by using sort of a magnifying glass, if you want to look at this real closely, a little bit of S was not an X direction or Y direction, it's some diagonal direction. But if I just expand this a little bit to make it easier to see, there was a dx component and a dy component, and a ds was what we're looking for. So you could use the Pythagorean theorem and do dx squared plus dy squared is equal to ds squared. And you can divide these things and simplify them in various ways to get a formula for ds. For example, if you divide everything by dx squared, you get the standard formula of the arc length is equal to the integral from a to b. These are x values, x equals a to x equals b, of the square root of 1 plus dy dx squared dx. So this is one way of simplifying this equation, dx squared plus dy squared equals ds squared. And by dividing by dx squared and then solving for s, right? So that's the equation there. And that is that's kind of a reminder of what you did before when finding arc length using an xy equation, using our Cartesian equation. This is not going to work for us because we have the t equations, but all we have to do is just modify our dividing. Instead of dividing by dx squared, we divide it by dt squared. And we get the equation in terms of our parameter t, which we get sort of t equals, I'll just say t naught, and t equals t1. I think that's the language they use in the book, of the square root of dx dt squared plus dy dt squared dt. So this is the one we're going to use for parametric equations. And it's really just a bit of algebra. You just take this thing, divide by t squared, you group them up, right? They're squared over squared. So dx squared over dt squared is the same thing as dx over dt squared. Dy squared over dt squared is the same thing as dy over dt squared. And lastly, this is just ds over dt squared. You square root both sides, you get rid of the dt, and you get our equation right here. So it's just a few steps, pretty easy. I don't think it's really that interesting to show, spend time in a video to show on something you're really never going to use again. It just comes from the Pythagorean theorem and simple algebraic simplification. That's all I'm just trying to point out. When we do section 10.3 and 10.4, we'll be doing another version of this using a different parameterization. And it's, again, the same algebra. Each time is the same algebra. All right, so let's do that let's actually solve the problem using this formula. So our arc length, our distance, is from T1 to T0 to T1, which is two different T values from 1 to 2. Square root of dx dt squared plus dy dt squared. Now, we've done dx dt before. I was on a different page, so I guess I have to do it again. Dx dt is this equation differentiated. If I take x equals t to the fourth plus 2 and it's differentiate it with respect to t, I get 4t cubed. So dx dt would be 4t cubed squared, right? The derivative squared. Then I have to find dy dt and square that, and then do the differential dt at the end. Dy dt we did do before. Dy dt is this one right here, 3t squared. So I'll just put the 3t squared in there. But it's squared because it's the dy dt squared. And that's my formula for the arc length of this parameterized equation from t equals 1 to t equals 2. And now it just becomes an exercise in doing the calculus. These ones can be very challenging, actually. 4t cubed squared is 16t to the 6th, and 3t squared squared is 9t to the 4th. And believe it or not, this can be done using a combination of trigonometric substitution and integration by parts, but it's a pain. It takes a lot of steps. So for these problems, I'm just going to recommend that you use technology to do them so that you don't spend a long time on this practicing old stuff. If you want to try it, you can try it that way. You'd factor out t to the 4th, and that becomes a t squared on the outside. Then you can use some trigonometric substitution and it turns into an integration by parts. Maybe a fun exercise for you if you like practicing those integration techniques. But I'm going to go to like Wolfram Alpha or something and just kind of do the antiderivative that way. So it's 16t to the 4th. Okay, so I'm not going to remember it. I'm going to pretend that I remember it, but I'm not going to remember it. So integral of square root of 16t to the 6th, maybe, minus, or not plus, I think, 9t to the 4th, maybe, dt from t equals 1 to t equals 2. You can type this out many ways. It's going to interpret it however you type it out as best it can. Let me see how accurate it was I typing in there. 16t to the 6th. Oh, I need a end parentheses. Well, I had the end parentheses, square root of that critter right there. So let me see if I typed it in correctly. All right, so this is 16t to the 6th plus 9t to the 4th. Oh, looks like I might have remembered it. Okay. It'll put it into some nice format just to make sure that you typed it into a way that it understands. I do believe that is our formula. And we get this marvelous answer in terms of inverse trigonometric or hyperbolic trigonometric functions, but we get a numerical result of about 16.592. So just try and demonstrate that whatever calculus we did before, we're still going to do, we have to modify our formulas a little bit because we have this other variable, this parameter t in there, that we have to be able to accommodate. All right, one last example for you before the end of the video, which is how to find the second derivative of this function. We know what the first derivative is. The first derivative we did before, so dy dt, if you remember, I think it was on the previous page. Yeah, on the previous page. Boom. It asks us to find the derivative of the equation represented by these parametric equations. So it's the same parametric equations for all the examples in this particular video. So we got 3t squared for our dy dt over 4t cubed for our dx dt, and that came out to be 3/4 t. So our dy dt, our dy dx was 3 over 4t. All right. So I'm just going to borrow that from over there. 3 over 4t. This is from example A. All right, so we got our first derivative. Oh, that's not my dy dt, by the way. All right, I got to slow down so I don't make those kinds of simple mistakes. That was dy dx. dy dx, the way we got dy dx, of course, was doing our dy dt over our dx dt. Okay. So we know what dy dx is. It's this guy right here. The question is, how do we find our second derivative? Well, we know the second derivative is just the derivative of the derivative. The problem is that we have our derivative in terms of t. We don't have our derivative in terms of x. So we're going to have to, figure out what to do based on this kind of thing right here, right? So we have our dy dx. We know that we can differentiate these things with respect to t because everything's in terms of t. So we're going to differentiate this function in terms of t to be able to find the second derivative. All right, I need to pause just for 1 second. Okay, so how are we going to find our derivative of our derivative equation? Well, we're just going to do our derivative that we know how to do, which is the derivative with respect to t. All right, so in the interim, I have lost my pen, so give me a sec. I'm really sorry to find my my stylus. Okay, so we're going to be able to take our dy dx function, and it's 3t, by the way, or 3 over 4t, and we can differentiate it, but the variable in dy dx is dt, as t. So we're going to differentiate ddt of our dy dx function. So we're taking the derivative of the derivative, which is going to give us a second derivative. The problem is that the variables don't match up. So once again, we're going to have to divide by dx dt. And let me show you what that looks like. If I take the derivative of y with respect to t, derivative of dy dx with respect to t, I get d dy, which is d squared y. I get dt dx. And if I flip this thing, I get dt over dx, right? I could take dx dt, I flip it to dt over dx and multiply. Then we have the dt's that divide out. And we have dx on the bottom, we have dx times dx. Dx times dx is d squared. So we got d squared y over dx squared. And as a side note, some of you may have been wondering for a while, why do we write the second derivative with the square in between the d and the y on the top, but after the x on the bottom? Like, it's not consistent in some sense, because the square on the top is in a different location than the square on the bottom. And that's because of how we're getting the second derivative. We're taking the derivative of the derivative. And ddy, the d's are multiplied or doubled up. So we get d squared. We get 2d's with a y. And then on the bottom, we have dx and dx, and that's literally 2 dx's, or dx times dx, which is how we get the dx squared. Anyway, just an aside for those who are wondering why that notation was chosen for the second derivative. Nonetheless, The second derivative, d squared y dx squared, this thing that we're looking for is given by this formula. You take the derivative of the derivative, obviously, right? That's how you find the second derivative, but you're taking the derivative with respect to t, and you're dividing by dx dt. Again, that's just the chain rule, or to get the dt's to divide out. So that's a formula. I'll write the second derivative over here just so that it's more compact for your notes. So the second derivative, which is d squared y dx squared, is equal to this formula right here. All right, let's go ahead and do that for this problem. So for our particular problem, we have the second derivative is equal to the derivative of dy dx. Now with dy dx, we have written over here already. That's just 3 over 4t divided by dx dt. We've done dx dt several times. Dx dt, if you want to look at it from above here, or we can recalculate it, it's just the derivative of the x equation with respect to t. It's just the derivative of x, which, again, according to our formula here, is just t to the fourth plus 2. So that's how you find the second derivative. You take the derivative of the derivative divided by the derivative of x. The derivative of the derivative is going to be respect to t. And actually, the bottom one, I have an x here. That's a mistake. Everything's in terms of t. All our parametric equations in terms of t. So we're differentiating dy dx in terms of t, and we're differentiating x respect to t. That's this formula right here. All right, let's just finish this up. I'm going to write this as 3 over 4 t to the negative 1, just so I can make sure I don't make a mistake on the power rule. So the derivative of 3 over 4t would be negative 3/4 t to the negative 2. And the derivative of t to the fourth plus 2, we've already done several times. That's 4t cubed. I do believe I could simplify this a little bit. Let's see, the 4 and the 4 are both the denominator, so it'll be 16. And I have a t to the 3 in the denominator and a t to the 2 in the denominator, so it'll be t to the 5th in the denominator, and that is my second derivative. Yes. Okay, well, there you go. There's a bunch of calculus using parametric equations. Same kind of process, but you do have to make sure that you update your formulas because we are working with the t variable, so everything has to be done in terms of t. And I did write out a couple of formulas that you might want to put in your notes about the formula for the arc length in terms of dt, in terms of the parameter, the first and second derivatives in terms of dt, in terms of the parameter. Okay, so hopefully this is helpful. Hopefully you will also reach out if you have any questions or any examples or what-if scenarios that I can help with. And as always, I hope you have an enjoyable day.